a lot of you may not realize that my PhD is actually in aerospace engineering. And so when I was hired here as a faculty of a marine science program, I thought I was a little bit of an anomaly. But now I realize I'm actually a trendsetter. Because Ben, so Ben here also has his PhD in aerospace engineering, and he has also recently been hired into a marine science program at Old Dominion as an assistant professor. I've known Ben for about, what, 6 or 7 years.
That's about right.
Since he started his PhD at the University of Colorado with a colleague of mine and Gary, Steve Narum. And he's taken something that I kind of started about 15 or 16 years ago and done much better stuff with it than I ever dreamed of doing. So he's going to be doing some, he's going to be describing his research on some of those most recent results and really looking at regional sea level change, looking at how much of it is natural climate variability, how much of it is anthropogenic, and using that to look for future sea level change. Ben.
All right. Thank you for the introduction, and thanks for inviting me to come here today and speak to you. So I am following in Don's footsteps, both in terms of career path and in terms of research. And today I'll be talking about regional sea level projections, and specifically in the contribution of natural climate variability to regional sea level change. So I was informed by Gary and Don, and I've read some recent news reports. There's some words that terms I should avoid. So I don't think global warming will show up anywhere. I think sea level rise might be a little dodgy, but I really couldn't cut that out without completely changing what I'm talking about. So I apologize if I offend anyone. All right, so just as a quick overview of what I'm going to cover today, the basic motivation for what we're doing here is on improving projections of regional sea level rise. So how can we get a better idea of what sea level is going to do in the future, not necessarily on a global scale, which is kind of the topic of pretty frequent discussion in the past 10 years, but on a regional scale. And I'll talk specifically about climate variability and how this affects sea level trends. And related to that, and this is the work that Don was talking about that I built upon, is on reconstructing sea level. So I'll talk about exactly what is a sea level reconstruction, why are we interested in doing sea level reconstructions, and how I've applied a slightly different technique to improve on some of the previous sea level reconstruction efforts. And then I'll use some of our sea level reconstructions to actually go in and look at the effect of climate variability on sea level over the past 60 years. All right, so why do we care about sea level? And I've managed to condense this whole thing down into one slide, so it took me a lot of thought. But more seriously, this is about why do we care about sea level rise here on the East Coast, where we are. And one of the reasons for that are these storms that come up the East Coast, such as Superstorm Sandy. So when we have higher sea level and we have these storms coming up the coast, it exacerbates the effects of these storms. You get much higher levels of flooding, coastal flooding. The effects of these storms are much greater. And you also have a higher recurrence time of these large storms. So if you have a higher foundation, essentially, for these storms to travel over, the impact is much greater, and the impacts you feel are these large storm events are felt more frequently. So this is just a picture here of Superstorm Sandy. And a growing concern in this region, and this is an approved term I saw for the state of Florida, is this nuisance flooding. And this is going to continue to increase. So as defined by NOAA, this nuisance flooding is flooding that causes public inconvenience and leads to road closures, damage to infrastructure. So basically, you wake up one morning, you have a road that's flooded, you have to take a different path to work. And that's something we deal with in Norfolk, where I am now. All right, so related to the storms, so here we have a map of, based on 2050 projections of sea level, every how many years will today's 100-year event occur? So you can see in many locations your 100-year event has now become a 20-year event, where I am in Norfolk. In some cases, 1 year, 2 year, 5 year event, in more extreme cases. So these large storm events are going to be seen and dealt with much more frequently when you have this increasing foundation of sea level. All right, in terms of nuisance flooding, so if we look at the return period in 1950, so this is how often we saw this flooding over a certain threshold. So this is the threshold set by the National Weather Service, I believe, for every one of these tide gauge locations. And basically it measured the how many years it takes to exceed this nuisance flood level. And you see back in 1950, we're seeing every 3 years, you're getting some nuisance flooding on average along the East Coast. And in 2012, what we're currently seeing is, in many of these locations, we're observing nuisance flooding multiple times a year. So tens of hundreds of hours every year, we're experiencing nuisance flooding in these locations. So when I was in Colorado, so this is a favorite of Steve Nerum, who I worked with at Colorado. I got the question a lot, why do we study sea level in Colorado? Well, for one, it's kind of a safe place. I don't really have to worry about the effects of sea level when you're in Colorado. And the other is maybe one day we're going to have some beachfront property in Boulder. Obviously, this is a little bit of a joke. But now, so this is about a mile away from my house. And this is since I moved there. So in the fall, there was a reasonable-sized storm that came up the coast, nothing too big. And now we get this flooding just in our streets. So this is an example of your nuisance flooding. It affects streets. It affects how you get to the grocery store, how you get to work. This is something that we're dealing with already. And I know Florida's dealing with similar impacts, just affecting day-to-day life. So while this talk is going to focus on projections into the future and how we can do better projections, this is already a problem in a lot of locations, and it's something that we're dealing with now. And I studied we bought a house in Norfolk, and I studied the flood maps very carefully to make sure it was a safe area. I think all the water from my property drains to this area, so I feel sorry for them. But obviously, as someone who studies sea level rise, it would really damage my credibility if my house flooded, or the street in front of my house flooded every week. All right, so global versus regional sea level rise. So global sea level rise since 1993, so that's the time period over which we have satellite altimeter measurements. It's been about 3.2 millimeters per year. And you hear this number talked about frequently. It's an easy way to communicate how sea level is rising, how the climate is changing just in the last 20 years. And since 1900, so using Reconstruction as a global mean sea level, this rate's closer to 1.8 millimeters per year. There's a little bit of range and different studies on that number, but it's generally around 2 millimeters per year, slightly lower than 2 millimeters per year. When we talk about global sea level rise, there's really 3 fundamental ways that you can change global sea level. You can have changing volume of existing ocean water, so you have thermal expansion. You can have melting from land ice or changes in land water storage, so basically adding water to the ocean. And you can also have changes in the depth of the ocean basins by movement of the Earth's crust, so glacial isostatic adjustment contributes about 0.3 millimeters per year to the rate of global mean sea level. Now, if we're talking about regional sea level trends, this is the map of regional sea level trends measured by satellite altimetry. And you can see some of these areas approach 1.5 centimeters per year, so much larger than this 3.2 millimeters per year. So if I'm on an island in the western tropical Pacific, this 3.2 millimeters per year doesn't really mean anything to me. I'm concerned about the 1.5 centimeters per year that I've measured over the last 20 years and whether this is going to increase into the future, whether it's a result of natural climate variability. Global mean sea level, while it's an easy way to talk about climate change, isn't really a useful metric for decision making and planning on the regional level. All right, so this is something that I worked on with Steve Nerum. He was giving a talk probably about a year ago, and he wanted to figure out a way to show in a very clear, simple example what contributes to relative sea level change. And this is basically as simple as we could make it. So you can see there's arrows all over the place. It's not that easy to condense down to a single graphic. But these are all the different factors that contribute to relative sea level change on a regional level. So we have to take into account all these different factors, have an understanding of all these different factors in order to get a good understanding of regional relative sea level change. If we break this down to a slightly different way, so here's another attempt at condensing this down to a simple equation form. So I've broken this out into 6 different factors. So we have climate variability, which is going to be the focus of the talk today. We have ocean dynamics, we have melting from the ice sheets, the mountain glacier, ice contribution, and vertical land motion, which is considered here to be negative. So subsidence is treated as a negative rate, and that's going to result in an increase in relative sea level. So you can argue on the sign on that. But anyway, if we're trying to accurately project future regional sea level, we need to have some understanding of all these different factors. And as I said, the focus today is going to be on this portion, the climate variability. And if we go back to the previous figure, so I've drawn a blue box around all the different factors that are affected by climate variability. So while I've separated it out here, really it affects all these different terms in different ways. And you see it's a big contributor to relative regional sea level. All right, so going back to the global versus regional, discussion. So if we're going to project regional sea level, we need to have an understanding of all these different factors on a regional scale. We need to be able to understand what they've been doing in the past and what they might potentially do in the future. And over a long enough period of time, the regional sea level trends will converge to a single value. So this map here, which is computed over 20 years, if I had this map, if I had satellite altimeters that were launched in 1800, say I went back in time, introduced that technology, launched some satellite altimeters, this spatial map would be really consistent. It would look much more like a single value. If the long-term trend is 2 millimeters per year, all these values would converge to roughly 2 millimeters per year. And you wouldn't have to worry about differences on smaller time scales. But we have 20 years of satellite altimeter records, and some of our tide gauge we have 20 years of satellite altimeter data, and some of our tide gauge records are very short, much shorter than 20 years. So you can have trends that show up that aren't really related to the long-term secular trend, the kind of the long-term increase in sea level, but they're trends that just appear because of your time scale. So you can have climate variability causing trends on time scales of 5, 10, 20, 50 years, so on. And as an example of that, so this is something that Phil Thompson, a recent graduate from here, and I are working on right now. So we've been working on looking at the tide gauges and the trends that you get from the tide gauges and how record length of those gauges affect the trend that you're able to estimate. So don't pay attention to these symbols. These are from 3 different reconstruction studies. But if we look at the number of tide gauges, so we were studying the time period from 1900 to present, and these are all the tide gauges within that period. And we computed the trends over the record length of each gauge. And all these gauges have different record lengths. Very few of them span the time period from 1900 to present. Some of them were only there for 10, 20 years. So you can see that even over the full length of the tide gauge records, we have big differences. So around Australia, we have very high trends. We have some larger negative trends in North America. And if we start to break these down into 20-year segments, so from 1930 to 1950, you get an idea of how many gauges were available back then, first of all. But if we start looking at specific locations, so let's focus on Scandinavia. So from 1930 to 1950, we have fairly moderate trends. From 1950 to 1970, we have negative trends. 1970 and 1990, we have very strong positive trends again. And same thing in these high latitude gauges here. In the Arctic, you have negative trends, very strong negative trends from 1950 to 1970. You have very strong positive trends from 1970 to 1990. So depending on the time scale, the length of these tide gauge records, you can get vastly different trends. And trying to get out an idea of the long-term trend from these is very difficult, and it's why we're motivated to do sea level reconstructions. All right, so we're going to focus on 2 specific areas related to the problem of projecting regional sea level. So one is improving and extending the past sea level record, and that's going to be done through sea level reconstructions. And the other is improving our understanding of the relationship between sea level and climate variability. So using these sea level reconstructions to try to pull out the effect of climate variability on sea level. If we can go explain the contribution, so what's causing the trend to flip from 1950 to 1970 between some of these gauges, we can remove that variability and get a better idea of the underlying trend in sea level. And both of these are ultimately in support of the goal of improving future projections of sea level, both globally and regionally, which I'll talk about more. All right, so let's start with the sea level reconstructions. So why do we need to improve and extend the sea level record into the past, and how can we actually do this? So this is similar to the slide I just showed previously, but just giving you an idea of the distribution of tide gauges. So this is from 1980 to 1989, this is 1950, 1959, and 1900 to 1909. And this is the number of gauges available in the PSMSL, kind of one of the main services for these tide gauges. The number of gauges that are available during these decades. So you can see in 1900, we have very few gauges and very few island gauges in the Pacific. Most of these are located in the northern hemisphere, as this shows, around heavily populated areas. The distribution gets a little better in 1950, 1959. And 1980, that's really the peak of our tide gauge coverage. And even then, we have huge portions of the southern hemisphere that don't have gauges. We don't have measurements there. You have large areas in the large ocean basins where we don't have measurements from tide gauges. So even in the best case, we don't really have very good coverage from the tide gauges. On the other hand, we have the satellite altimetry. So you have very dense observations over the whole ocean. This is the trend. I've already showed this, but the trend map you can create from satellite altimetry. And you can average all of these and get an idea of the global mean sea level trend, or the time series of global mean sea level with a trend of about 3.2 millimeters per year. But the big downside of the satellite altimetry is that record is fairly short. So you have a 20-year record. It only goes back to 1993. It's very difficult to get an idea of the low-frequency, long-period climate variability and how that's impacting our sea level using just this record on its own. So in a way to overcome the deficiencies of both of these two data sets, we do something called sea level reconstruction. So very simply stated, a sea level reconstruction is a data set with the record length of the tide gauges and the spatial coverage of the satellite altimetry. And what we do is we take the satellite altimetry data and we compute basis functions in some way. Don originally did it with empirical orthogonal functions. I do a slightly different version called cyclostationary empirical orthogonal functions. And what you do is you take those basis functions, so you compute dominant spatial patterns from the altimetry, and then you fit those to the tide gauges in some kind of weighted least squares or weighted fitting procedure. And most of the results here are going to be from CSEOF, which I'll talk about more in just a second. Sea level reconstruction that's now publicly available at NASA JPL PODAC. So that's the reconstruction I'll use for most of our results here, and it is publicly available. All right, so just briefly talk about EOFs. I'm sure a lot of you are familiar with EOFs. They're called a lot of different things. You can call them principal components. I'll just use EOFs, empirical orthogonal functions, for this talk. And in EOF analysis, you take space-time data. So you take data that has some temporal and spatial dependence, and you represent it in terms of what I'll call loading vectors and principal component time series, or PCTS. So your loading vectors are your spatial portions, your spatial patterns. Your PCTS are basically the modulation, the amplitude change of those spatial patterns through time. And you get a number of modes. So N here represents the number of modes you need to decompose your data. Often with the reconstructions, we limit N based on a certain amount of variance that we want to keep. You don't want to fit 100% of the satellite altimetry data to a handful of tide gauges, or else you'll overfit and get a lot of noise in your resulting reconstruction. But you're breaking down the data in terms of EOF modes. So each EOF mode has a spatial pattern, a loading vector, and a PC time series associated with it. And the underlying assumption with EOF analysis is stationarity. So you can see your loading vectors, your spatial patterns, have no temporal dependence. You only have the modulation of their amplitude through time. But any kind of propagating feature that you have is not going to get explained by a single loading vector, a single EOF mode. It will get split across a number of modes. So with EOF analysis and the stationarity that's built into it, it's difficult to capture propagating features, and it also increases the likelihood of mode mixing. So you're going to split a single signal, a wave, a Rossby wave, for instance. You have to use a number of modes in order to explain that single feature. And it's important to note that with EOF analysis, you're getting modes of variability that are data modes. And this is true not just with EOF, but also CSEOF analysis. So you have data modes, and they're not necessarily physical modes. So you have to go the extra step to try to explain these modes physically, to interpret them and make them useful for any of your analysis. And this is a little section from a textbook that I like. I've learned the following rule to be useful when dealing with advanced methods. Such methods are often needed to find a signal in a vast noisy phase space, i.e. the needle in the haystack. But after having the needle in our hand, we should be able to identify the needle simply by looking at it. Whenever you are unable to do so, there's a good chance there's something rotten in the analysis. So I think this is a good thing to keep in mind, not just with the EOF analysis, but also the CSEOF analysis I'm going to talk about. A huge sledgehammer to your data, break it apart into different pieces that you hope will give you a better understanding. But if you break it apart into a million different pieces, it may be a little difficult to interpret what you're actually doing. So this is just a general rule for being careful with some of these advanced data analysis techniques that I'll talk about here. All right, so CSEOF, so cyclostationary empirical orthogonal functions, are very similar to EOF. So you can see the equation, the basic equation is very similar, except now that your loading vectors have a temporal component to them. And this temporal component, these loading vectors, are constrained to be periodic with a certain nested period. So this D is what we call the nested period. So the nested period is something that you set prior to doing your CSEOF analysis. You should have some physical intuition or some knowledge of the data that you're looking at. So for instance, if I am looking at the sea level data, I know there's a strong annual signal within that. So I can select a nested period of 1 year. And the loading vector would then give you the 1 year periodicity. It would show you the change from warming in the northern hemisphere to cooling in the northern hemisphere, basically as the seasons change. That will all be represented in your loading vector. And your PC time series will describe the change in amplitude of the annual cycle over time. So basically the strength of the annual cycle. And each CSEOF mode is composed of 12 maps. So that would be one loading vector and one PC time series if we're looking at monthly data in a 1 year nested period. So I'll get to an example, and this will become much clearer in just a second. But as I said, that nested period is selected a priori before you actually do your analysis based on some information you have about the data that you're looking at. So I'll just skip to the example. So this is a CSEOF analysis of the Aviso satellite altimetry data. And this is your first mode. So this is the dominant mode that you get out of your altimetry data. And it's related to the annual cycle. So you can see up here what month this is for. And I'm just going to flick through them. So this is starting January, February, so on. You can see the propagating features within each individual loading vector. And you can see the warming that's occurring in the northern hemisphere. I'm going backwards now, just not to confuse you. You can see that sea level is much lower during the winter months, increasing. So you get a nice representation of the annual cycle. You have spatial patterns associated with this. You're not simply relying on a time series to interpret your mode. You have actually information spatially and through time that can then help you physically interpret your modes once you're done. So this goes back to the statement. You should be able to find the needle in the haystack. Having this extra information from the CSEOF analysis provides us a better chance of doing that. So now if we look at the PC time series, these numbers might be a little small, but you can see they're strictly positive. So this just tells you the amplitude modulation of the seasonal cycle through time. So as an example, say we're talking about the season here in Florida. Basically how cold the winter is, how warm the summer is. So if we look at 2007, you can see you have a peak. So this would mean that there was a very cold winter and a very warm summer. So you have a very strong amplitude seasonal cycle. Conversely, in 1999, you have the opposite. So a much milder than normal winter, a much cooler than normal summer. And when I take the average of all these maps and put them back with the PC time series, this is what you end up with. So you can see that you have your 1 year periodicity, which was built into this. So you get what you'd expect, your 1 year period back from your